China's latest lunar discovery has sent shockwaves through the global scientific community, reigniting interest in the moon not just as a relic of our solar system's past, but as a dynamic, active body with secrets still unfolding in real time. The findings, stemming from China's Chang'e missions, particularly Chang'e 5, have unveiled something astonishing: proof of active geological processes and the potential presence of a surprisingly young volcanic deposit, shaking the long-held belief that lunar volcanic activity ended billions of years ago. These revelations suggest that the moon's interior may still be cooling and evolving, and it's not the inert, geologically dead sphere we once assumed it to be. When the Chang'e 5 mission returned to Earth in December 2020 with lunar soil samples from the Oceanus Procellarum region, a vast, dark plain on the moon's near side, no one expected the data to upend decades of scientific consensus. But that's exactly what happened. Initial radiometric dating performed on the basalt samples revealed something extraordinary. The rocks were just under 2 billion years old, making them about 1 billion years younger than the previously youngest samples ever collected by the Apollo or Luna missions. This suggests that volcanic activity occurred on the moon far more recently than scientists thought possible, implying a previously unknown source of internal heat that sustained volcanism far longer than expected. But the real-time analysis didn't stop at the age of the rocks. Chinese scientists, working in collaboration with international teams, also began to detect unusual chemical compositions in the lunar soil. Unlike older basalt samples, the new material contained relatively high concentrations of thorium, uranium, and potassium, radioactive elements that generate heat through radioactive decay. This finding was not just a coincidence. It provided a compelling clue that these heat-producing elements may have allowed localized regions of the lunar mantle to remain hot enough to drive volcanic eruptions long after the rest of the moon had cooled. If proven, this would fundamentally alter our understanding of lunar evolution. Adding another twist to the story, high-resolution imaging and spectroscopic data from China's Chang'e 4 mission, the first to land on the moon's far side, began to reveal deeper layers beneath the lunar surface that appeared to be much more heterogeneous than previously believed. Some of these regions displayed signatures consistent with buried volcanic domes, glassy materials formed by explosive eruptions, and even possible signs of water ice trapped in permanently shadowed craters. These findings, combined with seismic data, suggested that the moon's mantle and crust were far more complex and active during its middle history than anyone had predicted. One of the most jaw-dropping findings came from the identification of exotic crystals in the lunar regolith retrieved by Chang'e 5. Among the minerals was a new phosphate compound scientists have tentatively named Chang'e. Why? A previously unknown lunar mineral containing helium-3, a rare isotope with tremendous potential as a future energy source. Helium-3 is incredibly rare on Earth but abundant on the moon, particularly in regions exposed to the solar wind for billions of years. Its presence in crystalline form, now confirmed by China's researchers, lends support to the idea that the moon may become a critical resource hub in the coming decades, not just for science, but for energy independence. This shocking lunar discovery is not only rewriting textbooks, but also reshaping global space policy. China's findings have prompted a renewed space race, with the United States, the European Union, and private companies like SpaceX accelerating their lunar plans. NASA's Artemis program, initially focused on a return to the moon, has now shifted gears toward establishing a permanent lunar base. The newly revealed geological activity, resource potential, and complex lunar history uncovered by Chang'e missions have made the moon a geopolitical prize once more, and China is firmly leading the charge. What makes this discovery even more impactful is how it connects to Earth's own planetary history. Scientists are now reconsidering theories about Earth's early volcanism and tectonic behavior in light of what the moon is revealing. Since the Earth and moon share a common origin, likely from a giant impact that tore part of the Earth's mantle into orbit around 4.5 billion years ago, any data about the moon's interior could provide indirect insights into Earth's early geology. The newly discovered volcanic activity suggests that the moon's thermal evolution diverged from Earth's in unexpected ways, perhaps due to size, composition, or tidal forces. Understanding why the moon retained heat in isolated pockets for billions of years could inform us about similar processes in early Earth or even other rocky exoplanets. Real-time analysis continues as China's robotic missions relay terabytes of data back to Earth, Using ground-penetrating radar, spectrometers, and thermal imagers, these missions are building an unprecedented high-resolution map of the Moon's structure. One stunning revelation is the evidence of a massive, previously undetected magma reservoir lying beneath the surface near the lunar South Pole, a region of intense interest due to its potential ice deposits. This subsurface anomaly, detected by the Chang'e 6 orbiter, may explain localized thermal hotspots, recent tectonic activity, and magnetic field irregularities. These findings could not only revolutionize our geological understanding but also pinpoint ideal locations for future lunar bases or helium-3 extraction zones. The broader implications of these discoveries are deeply strategic. China's National Space Administration has already proposed a series of missions aimed at creating a lunar research outpost by the 2030s. These would be robotic missions at first, followed by crewed missions, possibly in collaboration with other nations under the International Lunar Research Station framework. Meanwhile, NASA's Artemis Accords are working to formalize rules of cooperation and resource sharing on the Moon, which may become increasingly important as competition for lunar territory and resources heats up. While nations race ahead, scientists are urging caution and deeper analysis. The presence of helium-3, young volcanic basalts, and heat-producing radioactive elements on the Moon is only part of the story. There are still unanswered questions. Why are the volcanic deposits so localized? What allowed the Moon's interior to retain heat in just a few regions? Is the detected water ice truly accessible for future missions, or locked deep beneath impenetrable rock? And most intriguingly, could signs of past or even present lunar seismic activity suggest a form of lunar tectonics previously unimagined? China's discoveries are inspiring a new generation of scientists and astronomers, particularly in Asia. Universities across the country are now offering specialized programs in planetary geology, astromining, and space architecture. Funding has surged not just for national projects, but also for international partnerships. Meanwhile, commercial entities in China are already planning robotic landers designed to begin surveying and possibly collecting helium-3 by the end of the decade. If successful, this would mark the beginning of the Moon as an active economic frontier. The story doesn't end here. Chinese scientists recently teased that further analysis of Chang'e 6's returning samples, set to arrive in 2026, may contain material ejected from the Moon's mantle during ancient impacts. These deep mantle fragments, never before collected, could provide a direct window into the Moon's innermost secrets, including evidence of its core composition and heat flow mechanisms. If helium-3 isn't the only rare element present, if, say, other exotic isotopes or trapped volatiles are discovered, then the Moon might become even more critical to Earth's technological future. From a scientific lens, this shift in lunar understanding also hints at broader cosmic patterns. If a body as small as the Moon, once believed to be cold and lifeless, can retain enough internal energy to generate volcanic eruptions long after its formation, then what might we find on Mars, or Europa, or Enceladus? Could similar isolated pockets of geological activity exist on other moons or dwarf planets in our solar system? Could this explain surface anomalies, mysterious thermal signatures, or unexpected gas emissions detected by telescopes? The Moon is once again a proving ground, not only for technology, but for the limits of our scientific imagination. What we assumed was static and ancient is, in fact, layered with complexity. China's role in this unfolding drama cannot be understated. With every rock sample returned, every thermal scan completed, and every radar image processed, China is not only charting a path forward in space exploration, it's challenging the world to look deeper, think harder, and reach farther. As the rest of the world digests these lunar revelations, one thing is clear. We have barely scratched the surface. Beneath the gray dust of the Moon lies a history richer than we dream. Of fire, ice, and time itself. And thanks to China's bold missions, we are finally beginning to read it in real time.